Welcome to teaching session 3, which is on model life tables. And towards the end of this, we'll see how model life tables represent a category of relational models. In any case, I felt that for this teaching session, I was tasked to present something out of the demographer's toolkit that differs from conventional actuarial approaches to mortality analysis and modeling, in particular fixing crummy data, and something that was practical. In these symposia, we have had a lot of presentations of time series methods applied to the projection of mortality. This is not going to be another one of those presentations, because the first thing that came to my mind were model life tables. They're more fundamental. For smoothing noisy mortality schedules and filling in incomplete life tables, demographers will often turn to model life tables which embody global regularities. Now, demographers also use things like kernel smoothers, splines, and earlier generation graduation techniques. But model life tables are another approach, and they are used a lot. When I started at the Census Bureau in the International Center, I worked with an older fellow who predated the model life tables, and he said that when he started, when you had incomplete data for a country, you had to look for another country that was supposed to be similar that had complete data. And that was always something of a stretch. It was an ad hoc choice of the other country. It often really stretched the similarity, and the model life tables obviate that problem. Okay, so we'll go to our first slide. The model life tables express interrelationships among age-specific death rates at different levels of mortality. And when I say level of mortality, the concept is sort of the generalized height of the mortality schedule on the y-axis. It's sometimes summarized by life table indicators like life expectancy at birth or age 10 or something like this. In any case, model life tables are based on the mortality experience of a bunch of countries around the world. They're generally limited to countries with good data. And when you have a set of model life tables, it indicates how mortality schedules, by which I mean age-specific death rates, how they differ in terms of level and shape based on widely observed patterns, ideally globally observed patterns. And they're usually distinguished by sex. That's one of the most systematic variations in human mortality that there is. And they also often will include both sexes combined, just for the sake of ease, but they usually have separate series of life tables for men and women. Okay, what are they used for? Well, evaluating observed mortality schedules in terms of, do these data look good? Adjusting empirical mortality estimates when they don't. Filling in incomplete mortality schedules. And another interesting use is projecting the future development of mortality. For countries that are at intermediate mortality levels, this amounts to forecasting their future evolution of mortality following the collective experience that's already been observed. And that's a powerful rationale. For countries at the edge of the envelope, extrapolations have been made. That's always a little risky, But still, when you're dealing with a collection of countries, you can take a little comfort in the fact that you're not just extrapolating one instance. Now, I'm sorry this thing got out of control, but why are there model life tables? Well, many countries lack reliable vital registration systems. It's especially true in the third world, which includes most countries in the world. And then a lot of data everywhere suffer from age misreporting and other distortions due to measurement artifacts having to do with age. You have also interruptions due to catastrophes. For small populations, the data are often subject to stochastic variations, otherwise known as small numbers problems. And then model life tables are also useful for health-related analyses like the estimation of years of life lost due to excess mortality. It's always an excess relative to something, and the models can serve as a standard for what mortality would have been in the absence of the so-called excess. Okay, now the best and most recent model life tables around are due to John Ouellette and Associates, but I've forgotten. I should first have introduced myself. I'm Ward Kingkade, and this is my colleague, Nadine Ouellette, and I may ask her at the end of the presentation to say a few words on some of the databases that are used here. But in any case, the best and most recent model life tables are the Ouellette and Associates model. We'll give the citation later. This is called the log quad model because it's a two-parameter model that's quadratic in the logarithms of the mortality rates. It has two parameters, a factor h, which is the logarithm of the probability of dying from ages 0 to 5. The model also includes a parameter k that reflects the relative excess of adult mortality over what you would get knowing the h factor alone. And on the slide, you see the age groups that are given. They're generally 5-year age groups except for early childhood, where they distinguish the infant mortality rate. And then K generally ranges from -2 to 2 when you're dealing with countries in Western Europe and the overseas developed countries, by which I mean Canada, the United States, Australia, Japan, etc. If you were to throw in places like Russia, K is going to vary from something like -4 to 4. And when you let K take extreme values, you can capture some highly unusual patterns. Ouellette and Associates applied it to World War II mortality in Finland. Okay, Ouellette and Associates consider H to be their level parameter and K to be a shape parameter. The coefficients are estimated for both sexes combined on a collection of national mortality schedules from the Human Mortality Database. This database has stringent data requirements, quality requirements on the data for admission. The HMD data cover mainly Europe and overseas developed countries, and all data are subject to a standard methods protocol, which enhances the internal consistency of the data. I cannot overstate how important that is. And the data are very well documented, and Nadine can tell us exactly how detailed that gets to be. We'll say more about the HMD later if time permits. But I should mention that Nadine is the person who contributes Canada to the Human Mortality Database. Now, the coefficients are not really that important. We can just note that the VX column, which are columns 4 and 8, are 0 in infancy and at ages 90 and over, and then there is no value for ages 1 to 4. And that's because when you know the probability of dying from 0 to 5 and the infant mortality rate, that's the probability of dying from 0 to 1, you've already determined the probability of dying from 1 to 5. So they don't need to estimate it, and their software forces it to be consistent. This is the formula. When they're calculating the central death rate in the age interval 1 to 4, it also involves a factor 4K1, which is the average age at death in the stationary population from ages 1 to 4. And that's taken from an earlier set of model life tables. Okay, now we're going to look at some of the curves, plots of the coefficients. First, we see AX. This is the constant term. It's negative because the death rates are all under 0, under 1, and they're greater than 0. And the shape of this A factor sort of looks kind of like a mortality schedule, I suppose, if you exclude the sex differential. Female mortality is usually lower than male mortality at just about every age. And I should point out that these coefficients are estimated separately within the two sexes, so the sex differential doesn't need to be paid attention to. Then here's BX, that's the linear term applied to H. It also looks like an upside-down mortality schedule. If you picture rotating this 180 degrees on the y-axis, you'll end up with something that you might think looks like a mortality schedule. I'd still have trouble with the sex differentials in infancy and late age, but that's because the models are estimated separately in different exercises for the two sexes. Next we have CX. This is the coefficient of the quadratic term. And again, it sort of looks like an upside-down mortality schedule. I wouldn't pay attention to the sex differentials. Finally, we have Vx, which is the coefficient of the K parameter, and it's something that does not look like an upside-down mortality schedule or a right-side-up one. We see that it takes values of 0 in infancy and ages 90 and over. It's not ascertained at ages 1 to 4. You don't see a marker there. It reaches a peak for women in ages 20 to 24 and for men at ages 30 to 34. And it rises rapidly from 0 to ages 5 to 9, and then it stays pronounced until some age around 70. Okay, how do you fit the models? I've identified two alternative approaches in my explorations. One is to estimate the parameters h and k from two life table measures, and that just identifies the model. The software put out by Ouellette and Associates allows for 13 pairs of measures, and this approach may be preferable in third world countries that lack complete statistics. Then the alternative approach, well, let me just page over. These are the pairs of parameters that the software produced by Ouellette allows. One of the parameters is supposed to represent childhood mortality. The other one is supposed to represent mortality in adulthood. And the software will reject it if you put in two child mortality patterns or two adult mortality parameters. But they do give you some ways to back out of it if you don't have a 5Q0 or you're missing a 45Q15. Cases 9, A and B don't always converge. Okay, the alternative approach, number 2 here, is to accept the observed probabilities of dying in early childhood and to fit K to minimize a deviation function. This uses all of the available data, and it's probably preferable with high-quality statistics. That's what I've used it for. And this is the criterion. That's fairly straightforward. It's just the sum of squared differences between the logarithms of the observed mortality rates and the fitted mortality rates at each specific age. The lower the sum of squares, the better the fit. It's the least squares criterion in the logarithms of the mortality rates. Okay, let's look at some charts of mortality schedules. The first two are going to illustrate the effect of the K parameter. Here, the blue line is the observed mortality schedule. The red line is the schedule fitted on the sum of squares criterion. And here we see that that yields a K equal to minus 2.5. And then the green line indicates what you would get if K was equal to 0. So we see that the rates in adulthood in the green line are much higher than the other schedules. And the negative K is acting to pull down the mortality rates. And the red fitted mortality schedule conforms much better to the observed mortality. Obviously, we fitted to that. Next, we've got men in Scotland in 2016, and the colors are basically the same. 0 is the observed mortality schedule. Red is the fitted by the sum of squares criterion, and that gives us a K that's already about 0. And the green line here is what you would get if mortality, if the K parameter were equal to 2. In that case, again, you get higher death rates in adulthood. The positive K is pulling the mortality schedule up in adulthood. And it's sort of like a bow and arrow. It's reminiscent of that to me. Okay, we're next going to have an illustration of filling in 0 death rates in mortality schedules for small countries. Let's say you're the chief actuarial statistician in a small country where the annual death counts sometimes amount to 0 in some age sex categories. And you're tasked to prepare annual life tables because political high-muckety-mucks want to know life expectancy at birth on an annual basis. So you've got to calculate a life table for that. And you can try to reason with them. You can tell them that due to stochastic volatility, the annual data can have odd artifacts, and it's better if you group years together. But when you do that, their eyes glaze over, and they tell you, look, just give us your best estimate. Now, you know you can't show 0 death rates because there's always some non-zero probability of dying at any age. And in this situation, I might resort to a model life table. And so we'll look at some instances like that. Here are women in Luxembourg in 2014. The blue line is the observed mortality schedule. The red line is that fit on the sum of squares criterion. And the green line here is the schedule fit by the Ouellette criterion using either infant mortality rates or the probabilities of dying from ages 0 to 5, and also the probability of dying from ages 15 to 60. And what we see here is that we're missing a value at ages 10 to 14. The red line also seems to be closer to the observed data, at least at young ages. Okay, and our next slide deals with another case. This is Luxembourg women in 2012. Here the colors stand for the same things, but this population is missing death rates at ages 1 to 4 and 5 to 9. So now we'll see how we fix these. I should also point out here that it doesn't seem to matter whether you pick the red or the green line. They're both about the same. Anyway, here is the Luxembourg schedule, which has been fixed here. You see that the blue line at ages 10 to 14 coincides with the red fitted schedule. And you get a plausible pattern of mortality up to ages 10 to 14, but thereafter you get a very choppy sawtooth pattern. And you might be tempted to just take one of the model schedules. You may have a deviation from the observed rates in the very late ages. And then here's the case where we fixed Luxembourg women in 2012. Again, tying the observed zeros to the red sum of squares fit. And we get a plausible pattern here until ages 15 to 19, but then after that we get that sawtooth mortality pattern. These are stochastic fluctuations in a small country, and you might be tempted to just take the model. Now, the values in this worksheet aren't important. It's presented mainly so you can see that there does exist a bona fide spreadsheet for these calculations. And what the spreadsheet does is when the observed value of mx, which doesn't have a prefix, is 0, it substitutes the fit mx, which is that based on the sum of squares criterion. And that gives you the fix mx column. And if you can't see the individual rates, it doesn't much matter. I should point out that in this particular spreadsheet, the life expectancy at birth for the fixed schedule is 83.3. For the observed schedule with the zeros and all, the life expectancy is 83.4. And then for the fixed schedule, it's 82.6, the female life expectancy at birth. And so there's really not that much difference in life expectancy at age 0 between the different schedules. We also have the case of men in Iceland in 2014. It's got zeros at ages 1 to 5 and 10 to 15. And then here's where we fix that. The pattern doesn't look so bad until ages 15 to 19, but then you get a choppy sawtooth pattern. And the models here, starting at age 20, do have a decline in the death rates, but that's generally called the accident hump, and it refers to accident mortality at very young ages. Not very young ages, but young adult ages in the 20s. And we're looking at males here and not women, so we see that. The fitted schedules by the two different criterion are nearly identical, and you may just want to accept the model. Okay. So what are relational models anyway? They're called that because they relate one function or one schedule to another. And originally, William Brass proposed a relational logit model in which the cumulative probability of survival from birth to age X is related to a standard cumulative probability from birth to age X by a transformation that is linear in the logits. And lambda refers to the logit. The subscript or superscript S refers to the standard. We see the transformations linear in the logits, and what the logits are the logarithms of the probability of dying divided by its complement. That's an odds ratio. It's basically a logistic curve with asymptotes of 0 and 1. Now, the World Health Organization's system of model life tables is based on a relational logit model. It's extended to 3 standard schedules, each covering different sections of the age range, because there is no one-size-fits-all standard. And you end up in that system of model life tables with 4 parameters. In the Ouellette and Associates system, they treat 0Q5 as the level parameter, the probability of dying from ages 0 to 5. It's alpha in this system. They refer to K as their shape parameter. That's beta in the relational logit system. And they would say that the standard is what obtains when K is equal to 0. So that's how they reconcile their system with the relational logit model. And I'll point out that there is a citation. We'll come back to this so you can copy it. But I wanted to point out that there is a spreadsheet that implements this model. It's in Microsoft Excel. It's due to Griffith Feeney, and I give you his email, but you can get this by just Googling log quad. This will be one of the things that comes up. Feeney's spreadsheet takes observed values of the age-specific mortality rates and starting values of K and H as input. It minimizes a sum of squares criterion and the logarithms of the death rates. And you have to use the Excel solver for this. Now, how to get H, the logarithm of the probability of dying from ages 0 to 5, associated with a given mortality schedule, doesn't seem so hard to me. But the problem is how to determine a starting value for K based on just looking at a mortality schedule. That's not clear to me. And Feeney says that if you set K equal to 0, the spreadsheet will minimize the value of H for K equal to 0. So you can't use K equals to 0 as a starting value. You got to use something else. In my experience, fitting the log quad model to the human mortality database countries, if you allow the parameter H to vary, most of the time you end up with a value of early childhood mortality that's way too low. But Feeney gives an example for Swedish women from 1775 to 1779 that seems to work. Here, the probability of dying in early childhood, ages 0 to 5, is about 33%. The value of K is minus 0.38. The observed life expectancy for Swedish women in around 1775 to 1779 is 37.1, and the fitted schedule gives you 37.5. So he's worked that one out. And he has an explanatory PDF. It says some things I don't understand, but that may be due to typos, but it's there with his package. Okay, now let me briefly say a few words about the human mortality database. It contains age-specific mortality. It contains life tables. It has both period life tables and cohort life tables. It's got measures of exposure to risk. It's got some other population statistics like population size and the number of births. And it follows the standard methods protocol, which is reviewed periodically. It's highly selective on data quality. It has very few third world examples. It does have some data for Chile, but you might argue that Chile is not really a third world country. It's transitional. There's some data for Hong Kong, and you might make the same argument there. It's an urban population that was under British rule for a long time. And it includes data for Israel, but I don't think anybody is going to classify them as a third world country. The data in the HMD are meticulously documented, and Nadine may be able to speak to this at the end. What I want to say is that prior to the establishment of the Human Mortality Database by Ouellette, you had various collections in different places. The Office of Population Research at Princeton University, the United Nations Population Program, the International Program Center at the U.S. Bureau of the Census, where I started work, and the French National Institute for Demographic Studies, INED. And what you got with these collections were data of varying quality, calculated using different methodologies, and it was hard to reconcile one country with another, let alone one collection with another. And the HMD is assembled by two international teams and a large number of country specialists. There seem to be two nodes. One is the University of California, Berkeley, and the other is the Max Planck Institute for Demographic Research in Rostock, Germany. And it's my impression that the people in Rostock are doing most of the work. I should also mention that the Max Planck Institute in Rostock also has a life tables database, which incorporates a wider spectrum of countries. Now, there's no question in my mind but that this is a potentially highly valuable asset to actuaries and all others involved in mortality research. And now I'd like to yield the floor or the podium to my colleague to say some more about the HMD if I've omitted anything or said anything that's not correct.
So hello everyone. May we ask how many of you are users of the Human Mortality Database? Okay. How many of you claim that they are very knowledgeable about the HMD? How many have read the methods protocol? Well, that's good. Very good audience. Okay. Jean-Marc, can we access the website of the HMD? Because there are a few things I would like to show on the website itself. I will try to see. Yeah, I will try to see. You're not connected. All right. Okay, until the person gets here, I know he comes and goes. So, you've all used the life tables, right? This is perhaps one of the mostly used product of the HMD. And how many of you have used period life tables? Okay. Cohort? Mm-hmm. How many have used the actual death rates without any modeling? Okay, so the raw death rates. Mm-hmm. And how many use numerators and denominators of the rates? So that is death counts and population estimates separately, and you do your own calculation based on that. Okay. And how many use the raw data? So at the very end of each country page, you have the raw data that you can use. This is basically, if you follow the methods protocol and you use these raw data, you should be able, as long as you have good programming skills, if you're able to implement the methods protocol, you should be able to reproduce the HMD. So how many of you use the raw data? Kirill. Of course, I think we should add that Kirill has been one of the most important contributors at the beginning of the HMD and later on. My point that I think is a recurrent question that I get. So, period life tables, death rates at older ages are modeled using a simplified logistic model, which is the Kinisto model. So if you use a life table and you look at the column for death rates at older ages, these death rates have been modeled. And therefore, since probabilities of dying are converted, are basically death rates that have been converted, if your death rates are modeled at older ages, your probabilities of dying at older ages that you pick up in the life tables from the HMD are also modeled. If you want to apply your own model of old age mortality and you're not agreeing with the Kinisto old age mortality model, then you should use the death rates. So for each country page, in addition to having a line for life tables, you have a line for death rates. These death rates have been untouched in the sense that there is no model that has been applied to these death rates. So if this is what you are looking for, you should use that. Another question that often comes up is, what if I'm interested in cohort life tables? Well, if you're interested in cohort life tables, if you take death rates, cohort death rates, these have not been modeled using an old age mortality model. So if you want to use that, that's all right. Okay. Are there any specific questions with respect to the HMD? Just a second, yes. Are there any specific questions about the HMD, the use that how you use it and what you like to do, and maybe some things that you aren't able to do with the HMD? Anything specific? No?
We'll try to get you online.
Oh, yeah, you're trying to get me online?
Yeah, but you keep talking.
Okay. Just a second. The globe?
Blue.
Yeah, maybe the globe. Yes. Oh, yeah, meeting space. Go back, maybe. Yeah. Sorry. Wi-Fi, yeah, where you want.
Wi-Fi, yeah.
And then meeting space, internet. This one. Connect.
Could I ask a question
Yes,
during
sure.
the technical difficulties? I'm using more the World Health Organization data. How does that compare with the HMD? And for Canada and the US, should we use one or the other?
So you're using the WHO mortality database, right? So, of course, so are you using causes of death data? As you all know, in the HMD, currently there is no causes of death information. So it's total mortality, all causes combined. The WHO has the advantage of providing the cause of death mortality information. However, in the WHO mortality database, the data is provided for 5-year age groups, except at early ages where you have 0, then 1 to 4, but then you move on to 5-year age groups. And the last age group is an open age interval, which may start at an earlier age for some countries or some years. In the HMD, the difference with respect to that is for total mortality, you get single years of age. So if you're looking for a more detailed mortality schedule, you should then go to the HMD. The WHO doesn't have for the mortality database, it doesn't have the resources to have a single methods protocol for computing computing life tables. So therefore, they're relying on the statistical offices to provide them whatever they are publishing. And perhaps you may run into some country comparability issues, whereas in the HMD, there's a team that works really hard, both in Berkeley and at the Max Planck, to make sure that at least methodologically speaking, the life tables are built using one and a unique methods protocol, so that differences between countries in terms of life expectancy at birth, let's say, are not due to different strategies to construct or establish mortality, life tables. Does that respond? So, but at the baseline, I mean, both the HMD and the WHO mortality database rely on the statistical bureaus or offices which collect vital statistics or population registries data for countries which have population registers, and also census data for population sizes. Oh, good. Thank you so much, Karen. Okay. Yes.
If possible, can I ask a question?
Sure.
Jonathan from Energy Consulting. Sorry. The HMD, just to clarify, are any adjustments made for changes in fertility?
Changes in fertility? What do you mean?
For example, the rates that are displayed, are they adjusted for changes in fertility?
You're speaking about the HMD or the HFD? Because there's a human fertility database.
No, I'm talking about the HMD.
The HMD.
He may mean when the population is not stationary, especially in childhood.
Mm-hmm.
It seems like the answer is no, but okay, thank you.
Unless I am mistaken, I don't think that there is such adjustment that is made. Kirill, if you have perhaps...
Maybe 2 or 3 years, it was some adjustment to the method protocol to incorporate the monthly births.
Yes.
Okay. And for some countries, it's been probably incorporated to better estimate exposures for the death rates. But personally, I don't know how important is it. But certainly, it was. I guess it was motivated by the research in the United Kingdom. About some cohort mortality and changes in birth over time. So if you have such historical data, probably you can do better on estimating the exposures to compute rates. But how important, I don't know.
So, yes, please.
Also, the human mortality database does now have cause of death data for selected countries, for selected periods. So you can obtain that.
Can you speak louder?
Partially funded by the Society of Actuaries.
Speak louder. Yes, I can't hear you.
Partially funded by the Society of Actuaries, the human mortality database now does have cause of death data.
So, there are different projects by the HMD team that are ongoing, and one of them is to include causes of death in a database. There's also a project which with respect to producing a state HMD for the US. But I am not personally involved in these projects, so I cannot give you further details about that, but it's ongoing and it should be available. Yeah, yes. So maybe just quickly, and so this is the references. We'll come back perhaps to the questions regarding the model life tables in a bit, but since we finally got access to the HMD, just to make things more concrete, I guess. So here on the left-hand side, of course, you have the full methods protocol, and if you click on it, as Ward was saying, this methods protocol gets updated once in a while when there are important changes to be done in the methodology given the latest research findings. And it was updated last October 5th, 2019. And you also have one of the reasons also was due to work by Word in 2015 and Evgeny and Andreev. But okay, this is the methods protocol, and you have basically a lot of transparency. You can find everything that you may be looking for in this methods protocol. Then let me go on. So if you click on a country, let's say France. Okay, so you have. Is this pointer working? Yes. So this is the series you're at. So this is the France total population. If you're looking for civilian population for several countries which have been affected by the world wars, you have the civilian population if this is what you want to look at. But then what's most important is this. So you have your period data, and here your cohort data. And here at the very bottom is what we call the raw data. So you have births, and now Kirill was stating the births by month, deaths, population size, any territorial adjustment factors, if it's the case, notes, reference files. So this is the raw data. If you want to go back to that, it's available as a flat file. If you don't want to use the raw data and you'd rather use death rates, if you want to see observed death rates, this is the line where you have to look, the line that you have to use. Life tables, here it is. And if you're not interested in the deaths per se, but more in their numerator and denominators, then for numerators, you've got the deaths. If you want bilexis triangles, you get further detail here. And your denominator would be the exposure to risk. The difference between the population size and the exposure to risk is that population size are on a 1st of January. If you want to compute death rates, your denominator should be population at the mid-year, exposure, or more or less mid-year. So exposure to risk is a proxy for that. Okay? So that's it, the cohort data, as I was saying. So there's no modeling. So if you want just the death rates, you can use them, but there will be essentially the same as death rates in the life tables for cohorts. So I think unless you have more questions about the HMD, we should move on to any questions you may have about the teaching part of model life tables.
Yeah, I promised you I would let you copy the citation.
Jean-Marc, thanks. I have a question on the HMD. So every time the protocol change, all the tables for all the years are recalculated, right?
Of course,
right.
Yes. And maybe I will go back to the citation. Just one question here, one point. Ward was saying that for each country there's an effort to document whatever has been done with the data. But I think very few people read the background and documentation files for the countries that they use. It might be a good idea to skim it, at least. So the background documentation will give you all the information. So what is the initial source of the data that is used to make the calculations for that country? And if there's anything fishy in the data, any special manipulation that had to be done, it's meant to be documented here. So that's it. And of course, yes, each time there's a revision with respect to the methods protocol, everything is recalculated. So for Sweden, for instance, you have data back to 1751. If you have an update in the methods protocol in 2019, you will rerun all the scripts to produce everything that you see on the table for Sweden. That's it. Okay.
Yeah, I want to also point out, maybe most people in the room know it, but you can basically download the human mortality database.
You can show
Yeah, Nadine would be able to show you how.
A lot of people spend a lot of time trying to download each country one by one, or so here's zipped data files. You know, you can download the entire HMD right here. And it's organized by country and all the different elements for period, cohort data, and each element. And if you're only interested in, let's say, downloading not the entire HMD, but just death counts for all countries of the HMD for period data, this is your piece of information, and so on. And if the HMD gets updated and you'd like to use the newest data, then you just take all your folder for the all HMD statistics and replace it with the new one. So don't waste time, precious time, downloading piece by piece. Even if you're using only a few countries, it's probably faster to just download the entire HMD and have your program to pick up whatever you'd like to use.
Can I add something? I just would like to add that before release of the data on the website, it's usually run a program of the data quality checks. And data quality checks, it means that we plot the trends over time, age schedules over age, and compare the estimates in HMD with the external estimates, for example, from national statistical offices. For example, plots in the life expectancies and comparing with the life expectancies published by national statistical authorities. You know, in the whole report, it's about maybe 300 plots. And also, it's some notes on data quality internally was written before. You know, so all this data that are online, they've been checked before they kind of released to the public.
I think that we take these data for granted, but there's a lot of work that's been put into it. Yes, it's a very precious source of information, and I think that for many years, at least for the last 2 decades since the HMD made it online in its current format, more or less, a lot of mortality studies wouldn't have been possible without it, so it's precious.
I just would like to add some comment which may be interesting to actuaries and everybody else. We had a project which studied old age mortality, which was supported by the Society of Actuaries, and we compared old age data from the Social Security Death Index, which are individual records for everybody in this database, with the human mortality database data for old ages, and specifically age-specific death rates. And we found very, very good correspondence between both of them. And so it looks like almost exact correspondence between raw data of individual people from the Social Security Death Index and human mortality database, because both used the methods of extinct generation for very old ages after age 100. So this shows the accuracy of old age mortality estimates for old ages, but specifically for the United States. So this is what I would like to add.
Thank you.
Yeah, Kai Kaufhold from NMG Consulting. Well, thank you very much. I'm also a big fan of the human mortality database, and I was very interested to learn that demographers have a much simpler method of estimating tables or using much more sparse parameters than we actuaries do. One thing that I didn't quite understand yet, though, is how you actually combine or which countries you source the parameters from to fill in the missing data for example, for the missing deaths in the Luxembourg female children that you showed. So could you maybe explain more
Yes.
how you actually fit those parameters and how how you essentially borrow information from different countries to fill in information for small populations?
I'm glad you asked, because I was basically just standing up to speak to that point. Along with the citation of the article, which I suggest you read, because they answer the question of comparing their data to the WHO model life tables. They have a set of our programs available. It hasn't been worked up into a package because I don't think any of them have time for it. But that set of programs includes the program they use to estimate the coefficients. So you can choose any set of countries you want to estimate the coefficients from. I have basically left it to John Ouellette and Associates. I've used their selection of countries and their coefficients. But you may wish to try other things in specific cases. One possibility is, as third world countries transition and develop some sort of vital registration systems, they may be showing mortality patterns that are different from what's embodied in the model life tables. It may be that there are things in the European world and the overseas developed countries that are unique to that set of countries. So having the program that implements the methodology that developed this set of model life tables is very useful, and that is an asset of the Ouellette system. Well, if there are no more questions, then I'll close the session. Thanks very much for your attention and for putting up with my backspacing in the presentation. I hope that I've at least given you some idea of what the approach of model life tables involves. Thank you.